The purpose of the Scoped Emissions Trends page is to give an overview of your Scope 3 emissions and allows us to show how we can provide insight at a high granularity. For this demonstration, we will look at Category 1, Purchased Goods and Services, specifically focusing on embodied carbon, and Category 4, Upstream Transportation and Distribution, identifying upstream road travel. The purpose is to identify emissions from within the supply chain. The first thing to note on this page is the total emissions line chart, showing emissions over time. Our calculations have been made over Dynamics 365 data based on purchase orders, which contain details as to what good or service has been ordered, what the quantity of it was, and the date on which it was purchased. Using this data, we can see the exact days in which the emissions occurred and instantly identify any peaks in the emissions. Looking at the total emissions bar chart, we are also able to highlight where the calculated emissions data sits in terms of scope hierarchy. We are able to drill down and see the emissions from scope, down through category, down through subcategory, all the way down to the type of activity that caused the emissions. After joining this order data with vendor information and some spend data, we are also able to identify emissions based on the country of the vendor, which can be seen here. So how do our calculations work? For Category 1, we selected 3 materials from which to estimate embodied carbon, which were concrete, timber, and steel. For Category 4 emissions, we estimated carbon output from upstream road transport. For concrete embodied carbon, we first identified which records described concrete purchases based on the procurement categorization of orders placed within the D365 data. We obtained the quantity of concrete purchased for each record, in this case it was recorded in cubic meters, and then converted that cubic meter value of concrete purchased to kilograms using the ICE-DB averages. We then used DEFRA conversion rates to convert the kilograms of concrete to kilograms of CO2 equivalent. For timber, as with concrete, we first identified which records described timber purchases based on the categorization of orders placed, then looked at the dimensions of the timber purchased obtained from the descriptions of the order data to get a quantity of timber ordered. We converted those dimensions to kilos of timber, and then converted the weight of the timber to kilograms of CO2 equivalent using the ICE-DB averages. With steel, it was split across multiple categories. So here we identified which records were steel purchases using the description, and this time the weight of the total order was already in the descriptions. So we were able to use the ICE-DB averages once again to convert the recorded weight to kilos of CO2 equivalent to obtain an estimate. For upstream road transport, we used the D365 order data and joined with the vendor information to obtain the vendor location and the delivery address. We then determined the latitude and longitude of the origin and destination of the delivery for each order. We used the Open Route Service API to determine the distance between the origin and destination via road, and used EU regulation datasets for heavy-duty vehicles to determine an average emission per mile. We then calculated the kilograms CO2 equivalent based on the distance of the route taken for these vehicles. On this page we have cost versus emissions. As previously mentioned, we have used order data in our calculations, which has allowed us to identify the vendor within the supply chain and therefore link the total CO2 from our calculations directly to a vendor. As we also have a dataset of the total spend by vendor, we are able to join these datasets to provide a cost-based perspective, viewing the overall spend of a vendor against their emissions and allowing us the ability to split by emission source. This can be seen on the 4 visuals on this page, where we have the total emissions by total spend, the total emissions from concrete by total spend on concrete vendors, the total emissions from steel by total spend on steel vendors, and the total emissions from transport by total spend on any vendors making deliveries. On this next page, we have the year-to-date carbon dioxide emissions in kilos. Due to the granularity of our calculations over the dynamics data, we're able to view this on a cumulative graph and to show how emissions are changing over time. Currently, we are able to display these values by activity type, as shown on this visual at the bottom of the page, country, which can be selected in this left-hand menu, and vendor, for example, vendor 10. But with the correct shape of data, we'll be able to extend this to show cumulative emissions based on project, organizational unit, or any other business sector. This report is also able to be connected into live data and have the visuals update as the new data comes through, giving a near real-time emissions estimation. There's also the potential for adding emission predictions and forecasts here. This page is focused on embodied carbon emissions coming from concrete. The purpose of this page is to offer a tool for concrete procurement to determine the value of the carbon emitted by a vendor based on cost data. This top visual displays the equivalent kilos of CO2 emitted per pound spent for each of the vendors. In this case, the cost data we're using is the amount spent on each order, coming directly from the Dynamics order data. This means we're able to display these values using the spend amount that was recorded for the order and directly tied to each of that same order's emissions. For example, this vendor, ending 211, has the worst ratio with 14.27 kilos of CO2 per pound spent, whilst, for example, vendor 79 has 3.84 kilos of CO2 emitted per pound spent. This data is also shown in the scatter graph below to help highlight any anomalies or trends in spend data versus emissions. This is also a good time to note how this information can influence category 12 of scope 3, which is end-of-life treatment of sold products. Because we know the embodied carbon is considered to be in the product, if we break it down in the future, due to deconstruction, replacement, or other such reasons, we need to think of how it will be recycled or how much it will impact our Scope 1 or Scope 2 emissions when it's disposed of. So, this may be useful when considering switching to lower emitting products and vendors when considering what offsets you may need to make in the future. This page is focused on embodied carbon coming from upstream transport. Similar to the concrete page, we can see the kilos of CO2 per pound spent at the top. Below this, we can see a table displaying the most common journeys, or the highest emitting journeys. And on the map, we are able to see this information displayed based on each journey's origin. In this case, when kilograms of CO2 per pound spent increases, the size of the bubble is larger, and the closer to red the bubble is, the higher the number of total journeys from that location. This means that if there was a bubble that was both large and red, it would be a vendor of potential concern. On this page, we investigate the biodiversity of an area surrounding a vendor's location and the associated spend with that vendor. Vendor-specific biodiversity rates are obtained based on the location of the vendor within D365 data. We then map this location onto GloBio biodiversity data to obtain a biodiversity rating for the area of operation of a vendor. In terms of the map, the closer to red that a bubble is, the higher the biodiversity risk in the area, and the larger the size of the bubble, the higher the associated spend with that vendor. If we filter by purchase type and standard good, we can see the map update to show only vendors in this purchase type. Immediately, we can see that there are a number of vendors with high spend and with an amber biodiversity rating. However, we also have a data point in the center which has both high spend and high biodiversity. We can see that this data point is vendor 79, which has a biodiversity rating of 0.29. Comparing this value to the top right visual, we can see that this is at the higher end of the scale. And looking at this data point, we can tell from the contour lines that this vendor acts within a quarry, right next to which is the icon for a green space named Barden Hill, which is a national forest, an area of specific scientific interest in biodiversity, making this vendor potentially one of concern. If we instead shift the focus away from cost and onto carbon emissions, however, we now see a much starker picture. On this map, the size of the bubbles is now based on the CO2 emissions associated with that vendor, which immediately highlights vendor 79 as having very high emissions, and, using the table on the right, we can see that vendor 79 is the fifth highest in terms of total spend. From this information and that on the page before, we can therefore identify vendor 79 as a potentially high-risk vendor, as it is in an area of high biodiversity, has high spend, is directly adjacent to a national forest, and has very high carbon emissions, and is also performing quarrying activities. This insight highlights the potential benefit for a procurement team, as it will allow them to determine potential biodiversity risks of a vendor based on their location. On this page, we take a step back and look at the supply chain biodiversity from a more holistic perspective. Here, we have a country-level view of species information, which we use to determine biodiversity risk and categorize a country into a single, overall, red, amber, green status, calculated from the rate of species decline as a percentage, along with the endangered threat risk of a species within a country. The top left visual shows this overall biodiversity risk. This risk is made up of an average of species decline risk, shown in the top right visual, and the rate of endangered species, shown in the bottom left visual. Both of these are also measured as red, amber, green categorizations. These two values are averaged as ordinals to give a single overall risk value at a country level. If we take the United Kingdom as an example across these three visuals, we can see the overall biodiversity data, including the number of vendors within that country, along with some emissions averages. We can see the number of species and percentage of species decline within that country. And we can see the number of endangered species and the number of red list species within that country. In the bottom right table, we can also see how this all relates to vendor spend and vendor emissions within a country. As historical data has been collected, it is also possible to view previous years and visualize the change in RAG statuses across time. For example, looking back at 2018, we are able to see much lower risk values across almost all countries. This page could be particularly useful for providing a holistic view of biodiversity risk within a supply chain for annual reporting. On this page, we have a more focused view of the species at risk within a country. In the top left, we again have the biodiversity risk visual, showing the RAG status of a country. However, now when we select the country, we are able to see the breakdown as to which species have been identified and what their threat status is. Selecting the United Kingdom, for example, we are able to see the total number of endangered and critically endangered species being highlighted. And if we select those which are critically endangered, we can see the species and common names for those at risk, along with the total number of times they have been spotted in the occurrences. This page provides a holistic view of climate risk at a country level. The maps on this page show a red, amber, green categorization for flood risk, cyclone risk, and CO2 emissions by country. This data is visible on the table in the bottom right, which also includes the GDP risk of a country. Looking at the bubbles on the maps, data around the number of vendors and total vendor spend have also been included to give consideration into the amount of supply chain spend at risk from climate issues. Each risk factor here is shown by year and is both historical and forecasted. Forecasts for CO2 risk and flood risk go all the way up to 2100. Meanwhile, cyclone risk goes up to 2049. This allows for future consideration of revenue at risk based on supplier chain spend. Finally, we looked into the supply chain risk. Supply chain risk is made up of three factors: the climate risk, shown on the previous page, the demand risk, shown at the chart at the bottom of this page, and the risk of related news events, shown in the line graph in the center of this page. This supply chain risk metric gives a single holistic risk rating by procurement category forecasting a month ahead. The top visual here is the supply chain risk. This is a metric value between 1 to 6. On this visual, we can see how the model performed against the actual risk, and as we are still using the Dynamics 365 order data, we can see how the amount spent per month tracks against risk. This second visual shows the news risk. This is a metric between 1 to 3 and estimates risk based on the predicted number of related news articles for the month ahead. And this bar chart at the bottom shows the demand risk. This predicts the classification of volume of spend for the month ahead. The performance of the models can be seen in the cards in the top left. On the map in the bottom left, the bubbles for each country are larger and more red the higher the supply chain risk, and hovering over a country allows for risk factors to be shown in the tooltip. If we wanted to select a specific month, we can see how the predicted values change for the chosen month. Additionally, if we select a single procurement category, for example, pipes and fittings, we can see how all risk metrics change to show predictions relating to this category. As this model calculates supply chain risk a month ahead, it can be used as a tool for procurement to determine the relative risk and to act as an impact factor when considering vendors and future purchases.